This is the Big Island Amateur Radio Club's TechNet, and this is a hybrid session where we're going to be working here tonight on Zoom, and we're going to be looking at a little bit of antenna modeling. The program that I'm going to be showing tonight is EZNEC, or EZNEC, and I've got the purchased version, but there is a free version available that has a limitation as to the number of wires that you can have, and the number of wires is going to make sense as we proceed a little bit. So first, I'm just going to open the program. Here's the icon over here. I guess this is supposed to look like the far field, which we're going to see a little bit. So I'm just going to go ahead and click that and open the program, and I'll have to drag everything over to the display space. So when it opens up, I only get two windows at first. And it's these two windows. So it doesn't look like you're doing much yet, but there's a lot more going on here. The first thing is almost always, and I think actually always, is going to open to last.ez. So this is the file you're working on. And this is literally just the last antenna that you worked on. It doesn't open to a blank workspace or anything like that. It goes to a separate copy of the last antenna you worked on. I don't even remember the last antenna I worked on. Okay, so it looks like I was doing some simple stuff with a vertical and some radials here. And I can tell from looking at this that I had an L network in here, so I was doing some matching work and stuff like that. So if I want to open something new, this program doesn't have anything up here in File to go up and go to New. The only thing you can do is edit existing files. It's a shortcoming of this program that a lot of us have brought up many times over the years, but I don't think it's going to go away anytime soon. So you can simply take this last file you're in and move on from there, or you can open another one of the existing files. And the program comes with some files, and you're going to see I've got a lot of other files in here too. And you could just open any of these files. You know, there's some dipoles and stuff in here that you could open and get started with. But just the takeaway from this is that you're gonna have to open a file or start with the last one that you worked on and then modify it to get moving. So when you want something new, find something that's close to something that you want to work on. So I can go back and open that last one I worked on, and then start from there. You're going to delete wires and you're going to move forward. So to see your wires, you double click on that wires line, and here's the list of wires in here. So that's a lot so far. I mean, it's sort of an odd way to interface with a program. You can't just create a new file. You've got to modify an old one, but there it is. So we're going to just make an antenna from scratch here. You can delete all of your wires but one, and I'm going to do that now. Take the multiple select, try this again, and I'm going to delete them, and okay, we're down to one wire. And I've got also one source in here, and that source is going to be, think of it as your radio, but it's the feed point of the antenna. So right now, I've got one wire in here. It starts at 100 inches off of the floor, and it goes up to 100.25. Now, you don't have to do things in inches in here. I'm doing things in freedom units because that's what would be familiar to you guys. You can come in here and you can change your settings around. You can do it in meters, millimeters, wavelengths, which can be convenient for some things, but I don't actually find to be ultimately that convenient. So pick a unit of measurement that is comfortable for you. I'm going to stick with the freedom units because I think that's probably what the group here is going to be most familiar with. But there's other things that you need to check too. So for your models, you have to check a step size. Right now I'm set to 1. I'm going to go back to the default, which is 5 degrees in the step. And that's going to make some sense after we run some SWRs and look at some far fields. But you also have to choose your ground type. So you've got various types of grounds. So right now we're just thinking about just getting started. What can we do to move forward? If you model in free space, things are going to make a lot more sense as they would look in the ARRL antenna book. But they're not necessarily going to be what you would expect in real life. So let's take a look at that. So right now, I just want to make an antenna. I don't really care what it is. So I'm going to take one wire and I'm just going to make it 40 inches tall. So here is that wire. I can bring it in. We can look at it a little bit. And these red lines here, these are the axis lines. So if I offset my wire a little bit, and what I'm doing is I'm drawing by numbers, which is easy for some of us who've done AutoCAD and not so easy for others who haven't. So I'm actually going to offset further than that so you guys can get a clearer view. Okay. And since I don't have anything else in the model, you don't have a relative space yet, but we'll get there. So this is a wire, and here's a source. I know that because I know the symbol to be the source. But you notice it's not in the center. I opened an older model. So now I have to deal with the settings I had in the old model. And in that case, I wanted the source out towards the end. But now I don't. So I'm going to say put it right in the middle, 50% of the length. And here it said, well, I can only give you 25%. That's a little weird. So we're going to go figure out why. And that's because I don't have enough segments. So this is an important concept when you're modeling. You have a wire, but that wire isn't just one wire because we're doing what's called methods of moments calculations. So a line is an infinite number of points between two places, but my computer can't calculate infinite. It'll take it infinitely long. So I need to break it up into manageable pieces. And the pieces we're breaking it up into are segments. So 2 segments, that's not enough data resolution. So I'm going to increase that. And now you see all these green spots showed up here. These are all the individual wires that the computer is going to calculate the currents and magnetic fields in as it does its thing. And now I've got enough segments that it's saying, okay, your actual position of your source is now smack dab in the middle of that wire. The number of segments you have in a wire is going to be the make or break, and we're going to get into that later. But just be cognizant. You have to have enough segments, but don't you dare have too many because, man, the program will complain forever. And we're going to show you what those failures look like. So what have we done? We now have one vertical wire sitting here. We've got a source, a feed point right in the middle. So this is like a vertical dipole, half of it above, half of it below. So in theory, this should resonate at a frequency. So if we come over here to this SWR button, and I got to drag everything over to the workspace here, and I'm going to tell it that I want it to sweep from 100 megahertz to, well, let's go with 500. I'm going to give it a fairly big step because we got a lot going on there, but it's a very simple model. It should go pretty fast. And it is over here running away, calculating the currents, and it popped up this screen. So this looks very much like what it would look like if you had a VNA and you hooked that vector network analyzer up to your antenna. This is an SWR. We're familiar with these measurements, right? You want an SWR that's as close to 1-to-1 or 1.1 to 1 down here. So it says that I'm resonating at 140 megahertz and I'm resonating at 430, 440 megahertz, roughly, because I've got relatively low resolution here. So this would be the quarter wavelength of this wire, and then this is a 3/4 wavelength, because at every odd integer multiple, your wavelength's going to be resonant. The pattern may not be what you want, but it's going to be resonant. So for the ham band, I'm not exactly where I want to be. I can already tell that. So let's just shorten this wire up an inch. And what I did is, these are Z calculations. I started my wire at 100 inches above the ground, and I was at 140 for the top. Now I'm 139. It's an inch shorter. So now if I run this again, there. So 150, and the reason it's cut off like this is because I'm only doing the calculation in these 5 megahertz steps. So now I can see this is roughly where it's tuning up. Let's take a closer look down here in the 2 meter band and see what it's doing. So to do that, I'm going to hit the SWR button again. I'm going to close this because you're going to see in a pop-up you're always going to get. You're going to see this all the time. I already ran SWR sweeps. Do you want me to do it again? Well, I don't want to see the data I did. No. So I'm going to show me better data. So now I'm going to say, let's say 140 to 150 and let's go 1 megahertz and it'll run fast. And boom. So here's an SWR sweep that shows what our antenna is doing in frequencies that we're actually licensed to use. So I can tell that the actual resonant period of this antenna is somewhere between 144 and 145, but it's under 2 to 1, all the way from 140 to just below 150 megahertz. Why didn't it come all the way down? Well, I can tell you that right here, it's close, but the actual feed point impedance is 72 ohms. That's what the Z means. And here's our phase angle. So you guys working on your extras have heard about phase angles a lot. It's actually telling you your phase angle right here. So we've got a real ohmic resistance, an impedance, real impedance, 72.02 ohms, but we've got a 0.04 phase angle. So that's actually like nothing. This thing's great. We're not too inductive, we're not too capacitive, but I can tell you that it is just slightly inductive at that frequency. And I know that because I've got a positive J instead of a negative J. And you guys will remember when you were studying, when we're looking at impedance on the Cartesian axis, and they tried to make sense of that. This is where that starts to come into play. But don't get lost in that. Really, when you're just playing with this stuff the first time, you're just looking at this curve and saying, okay, does it match? Yes, no. And then once you're a little bit more comfortable, you're going to start looking like, okay, I'm in the right resonant window, but what can I do to lower this SWR further? And that's where you're going to start to rely on these numbers. Now, if you were just trying to set something up in an emergency to have emergency communications, I took my radio up to this and talk all day. A 1.44 to 1 SWR works for me. It's going to get out. But I want to see how well it's going to get out. Now, we've got near field, far field, and far field plot and all of that. At first, the only one that you're really going to worry about is your far field plot. Near field, far field tab, stuff like this, I really use those heavily, but don't get lost in those at first. Just stick with the SWR and the far field plot. So when it calculates the far field plot, it's going to take this frequency that I put up here, and it's going to calculate this pattern. So this is roughly what the pattern radiating from the antenna is going to be. Now it's kind of blocky, and it's hard to make sense of. Now I can say I want to see the azimuth slice, and this is the peak of the azimuth gain right here at 50 degrees, and say, show me the 2D plot instead. And the reason I'm getting this 3D plot is because I told it this is the plot type I want, is 3D. I prefer 3D because I can always get the 2D plots right out of it, but you can't in this thing go from a 2D plot to a 3D plot. So that's why I started here. And these, we'll get into this a little bit more, but you can take a slice of your antenna and see on this plot what the gain at that elevation is going to be. And you can look at different directions. Now this isn't very exciting for a dipole. When we look at some other antenna designs, it's going to make a lot more sense. But this 5 degree of resolution, it's really great for quick stuff, but I find that the actual resolution isn't that good. And that's why I had this set to 1 degree, which is the minimum that this thing's going to allow me to do. So now if I rerun that plot, there's a lot more resolution there. So there's a lot more I can see. So you can see that as this thing goes up, it's got these fanning cones of signal as it goes up, and they're nested within each other. So when we look at the azimuth slice, you know, as I go down here, you're going to see the red ring right here descend. It's going to show you what level of the model you're at. And then you can correlate, and you can actually work out the gain here or just read the numbers. Still not earth-shattering yet, but this is just the very basic operation of the program. So again, we had to use an existing file. We used the last one we worked on. we started editing wires, and we punched one in here. And we've got a source, because you have to have a feed point. And we're going to worry about the phase and the amplitude and all that later. The defaults are going to work for most everything you need right when you get in. But so that was 446. Let's actually look at the 2-meter band where we were looking. How does this thing actually perform in the band we were interested in? So this far field plot is based off of the frequency number here. There's a couple of things that this frequency does. It doesn't come into play for that SWR at all. But here, this is where you need to set the frequency that you're intending to analyze your antenna at. So now I moved it to 146, and you'll see that the plot is much different. So here, I can, again, select my azimuth slice, which isn't going to be very exciting on a dipole because it's not doing much. Well, let's take a look at that elevation slice. This may be a little bit more interesting because this is the typical dipole pattern when it's above the ground. And here you're going to see that you've got a peak gain at 8 degrees above ground level. So the elevation takeoff angle for this dipole hanging out there above the ground is 8 degrees. And it's given 4.1 dB of gain. Now, why would that be? It's a dipole. Question for the group. How much gain, isotropic gain, does a dipole normally have?
2 dB?
Yeah, roughly 2 VD, 2.15 dBi. So why do I have 4.1 dB of gain showing here? 2 reasons. Never trust the gain numbers that a computer program spits out at you. And the other reason is because I've got a reflection from the ground. So we're going to go back over here to the ground. And I said, remember, free space, you're going to see things that look a lot more like they were in the book. So I just changed my ground type to free space. And now when I run the plot, that looks like a dipole. That looks like what you saw in the ARRL antenna book. So in mathematical theory, this is the pattern that you're getting out of your dipole. In real life, it's not. So right now, if I look at this azimuth slice and I say, what was I getting? Oh, I'm getting that 2.11. The only reason it's not 2.15 is because this antenna is resonant at 144 and I'm at 146. But yeah, that's your dipole gain right there. Once you add other things in the environment around your antenna, it gets different. So let's add the biggest thing around our antenna that affects it. We're going to add it back. Well, first, let's go with that perfect one. I don't know why this is in here. It's absolutely useless. But when I run that far field plot again, it's going to be way overly optimistic because it's going to say that the magnetic field in the ground is causing 8.16 dBi of gain. Nobody has an absolutely perfect, rare earth element magnet that they're operating their antenna on. So I don't know why it's there. Don't use that for most of the stuff that you're doing. So here that leaves us with real. The ones that you're going to use, free space occasionally, because you're going to try to make the pattern look like something that it looks like in the book. And then real, and then you've got 2 choices, high accuracy and mini neck. So high accuracy is the default. And high accuracy is very good for ground reflections. Mini neck, however, is a different type of ground plane in the program. Now, NEC, this is EZNEC, is the numerical electromagnetic code. It was originally a Fortran program that was put together to do methods of moments calculations for magnetic fields. Method of moments is nothing more than statistics. And it's a tool in statistics where you say, look, I can't calculate every possibility in an infinite system. So that's why we have segments. We're calculating it here and here and here and here, and we're extrapolating what is between them. That's our method of moments. So we check it at this moment, and we check it at this moment, and we check it at this moment, and we extrapolate what it's probably doing in between. So when you use your ground, this one that was in here, wrong line, when you in here and you had mini neck, I can't remember what the mini stands for, but it's a different method in the code of handling the currents through the grounds. And what this does is it allows you to use the ground as part of the antenna. So let's do that. Well, I'm not going to change it yet, but I'm going to say, okay, I'm now 0 and 39. So now it says here, this wire is connected to the ground. And theoretically, everything should be good, right? Because I've got essentially a monopole antenna, like a mobile on a car. If I run the SWR, something's not right. So why is that? Well, there's going to be a lot of things, but you notice right here we got a warning. The wire is connected to a real non-mini net ground. See the manual. So I will tell you, the manual for this is very helpful, but my God, it's one of the worst things I have ever tried to read in my life. I've referred to it for a few pieces, and for the rest of the time, I just refuse to go into the thing. It's here online. It's very long. It's very thorough. It's a PDF you can get to. Just Google EZNEC manual. You're going to go to that page. Let's get what format do you want and what size do you want. So here's just a regular printable on letter paper PDF format. If you ever have insomnia, it's the cure. It's god awful. But that's because electromagnetics is complicated. But it's there. If you really need it, and I don't have the answer, somebody else doesn't have the answer, it's there. So it says don't do that. So, okay, I'm connected to the ground, and I'm going to choose the mini neck. And then let's try it again. Now, spoiler alert, it still ain't right. So here's the biggest thing. You can't calculate radials on the ground, or antennas on the ground like you would use with radials, just by attaching the antenna to the ground. You're going to get unpredictable results. So I also erred when I did that because I didn't move my source. So let's go ahead and do that now. And I'm going to say I'm going to go to 100% towards N1. Nope, that was 0% towards N1. There you go. So now it's at the bottom. And I actually needed to cut this down in half, and now I should be able to run it and get a reasonable return. So there we go. I didn't get the alarm saying don't use non-mini net grounds when you're attaching it to the ground, and here it is. It's looking like it's working, but I will speak from experience, don't do this. You will get weird, funny returns. So how do we get around that? Well, this program has some good features built into it. So what I'm going to do is I'm going to raise this thing up slightly. Let's say 1/2 inch. And I got to raise the other end slightly too. And I'm actually going to raise it 3/4 because of where we were. So now I'm going to give it some radials. So I'm going to say the center of my antenna is 10 inches, and 0.5. So that is the point that is the bottom of my antenna. And I'm going to go out, I'm going to leave it in line there, but I'm going to add 19 inches, so that'd have to be 29. Drawing by numbers is something that's going to be easy for some people and not so easy for others. But now I'm going to take the other end and I'm going to make it 0. And I'm going to cut down the number of segments because segments are sort of an issue here. Well, gee, things just got really weird. So let's figure out where I went wrong. So it's because I punched it into the wrong field. There we go. So now I've got my one wire facing up and I've got my one wire facing to the side. Now that I've got 2 wires, you can see that I'm offset from the 0 point in this model. And I do this a lot because I don't want my poor old eyes to see these lines and think they're antenna elements. So you don't have to offset your models from 0. You can leave your X and Y 0 for your starting point. I just don't, because I have before, sitting here at night, mistaken these for antenna lines. So I've got this one radial here. It's in contact with the ground on this end. I know that because it says that that end is in contact with the ground. And then it is in contact with wire 1, end 1 on its other end. So this is wire 1 and end 1 right there. These are actually electrically connected according to the model. I don't need to add a source to this because this source right here is already the feed point. So right now, if I run my SWR, I ought to get something, it's kind of weird. So let me figure out what I've done wrong. Did I detach something somehow? All right, bear with me. Got one wire in, it's oh. Because I was still zoomed way in. So let's see where this thing is sitting for resonance. There we go. It's way down here. Now, there's a lot of reasons why it did that, but just know that as you modify your antenna, you're going to get unexpected results out of it. A couple of big reasons for that are usually to do with what you're doing. It's rarely the computer, but I'm going to show you a couple of gotchas later where it does happen. But the reason why I got that is because I'm connected to the ground here. Remember when I said you're going to connect to the ground and it's going to mess you up? So I connected this wire to the ground and suddenly this radial is really long. So if I raise that back up, so now it is no longer in contact with the ground. You see that wire is open and we run it again. Boom, it put it right back where we are. So remember, if you connect it to the ground in this program, weird things will happen. So that was the only difference there. There was no real difference to the length. The only difference is it was connected to the ground versus it wasn't. So one of the best takeaways I can give you there, keep the things off of the ground. The code doesn't like it. So now we need radials because we can't use the ground. I don't want to have to type in all of those radials here. Trivia question, what is the optimal number of radials for a vertical?
32.
120. So after 120, you no longer see a statistically significant increase in the efficiency of the antenna or any appreciable change to the far field pattern. I don't want to put in 120 radials into this thing. Fortunately, it has a tool for that. So I'm going to come in here and I'm going to highlight the wire I want to use. And I'm going to say create radials. So, okay, let's just start with 4. A lot of us have antennas that have 4 radials. There we go. So now let's take a look at that SWR again. Hey, look at that. Much better than when it was in contact with the ground. You also notice here, just from the design of the antenna, that even though its resonant frequency is just outside of our band, I could bring it down, but this is just where we're playing around at the moment. And its impedance is now much lower. So this confirms what we already know from antenna design. A dipole has a characteristic impedance of about 70, 75 ohms. If you bend the dipole, that impedance changes. So that's why your V antennas have a 50 ohm impedance, is because you've lowered the radiation resistance by bringing those elements closer together. Well, now I'm at 90 degrees, but I added a whole bunch more elements. So this thing can conduct to itself very easily. So now we're at 38 or 39.8 degrees. So we're matching better, but we've gone too far in the other direction. So how do we take a vertical and tune it so that its feed point impedance is closer to 0 degrees? What can we do with it, or its radials, or anything like that? I'll skip ahead and say that we can angle these radials. So to draw, we're going to come in here and I'm going to find my wires screen and I'm going to move up. So right here, I'm a 1/2 inch off the ground. Well, let's add 3 inches there. And I'm going to lengthen us a little bit there. And then I've got to move each one of these on its near end to 3 inches. The other way I could do this is just to delete them and move forward, but I don't want to do that. So now if you look over here at my drawing, they're all touching again. If we look in here, they're all connected again, but now we've got that slope going on. So now when we run that SWR again, oh, look at that, our bandwidth increased and our impedance is closer to 50. And I'm pretty sure that if I actually narrowed that up a little bit, which I'm going to do now that I'm done making that point, let's see. There we go. So right here, 46, that's not bad. 144 right at the bottom of our band. We got a 1.1 to 1 SWR. So we just designed an antenna. It's for working in the bottom end of the 2 meter band, and it matches up nice. It's a little bit low on frequency though. How do we raise that frequency? Well, that's antenna basics. We're going to shorten that wire again. How do I shorten it? Again, it's with the numbers. So let's go a little bit shorter. We can run that SWR again and see what we got. There we go. We moved up to 145. We still got that 45.46, which isn't bad because when we stray further away, look at that. So further up in the band, we've got 50 ohms. So this is a perfectly usable antenna right here. You could make great contacts on this thing. So let's recap real quick what we've done. We opened a model. We put some wires in. We set a source where we want it. We made sure that we had enough segments, and we got it working in the frequency range we wanted by drawing by numbers and getting the length to where it was appropriate. And we added some radials, and we made sure those radials weren't touching the ground because that's a no-no here. Our step size, we reduced to 1 degree because that's my preference, because when I see this far field plot, I want to see something I can actually understand. And then we looked at how to look at your azimuth slice, your elevation slice, and then here we can see that your peak gain is up there, but you're usable down here. You're only 4 dB under your peak, so still quite usable. But we learned how to look at those things. There's a lot of other features in here. I can change my wire loss. I can hit that button and come over and say, I'm going to make this thing out of copper. And that's going to change how it performs. I can change the ground description if I want to. And I can actually punch in the information. I can put insulation on my wire. So I can say, okay, my dielectric constant is going to be 3 because I'm using something like a polypropylene, and it's going to be, let's say 20 thousandths thick, or 20 thousandths thick. And now I can come back, and so there's a lot that you can do in here, just don't get lost in it. This is stuff that matters later, not earlier. Did it make a difference? Oh yeah, because of course we increased or I should say we decreased our propagation velocity. The electrons are no longer moving through that wire at the same speed, so we were able to shrink that wire up in size. Important when you're designing antennas for HTs and stuff like that. You want to make it smaller. You can throw a little bit of insulation on it, and the program accommodates that. So again, these are just the very basics of the program. So let's go ahead and look at saving. Save as, and window pops up, and if I do this, it's just going to overwrite my last. So this is our TechNet antenna. I'm going to save it that way. Save. If I make any changes, it won't automatically save it. and I can't click save. You notice there is no save button. So let me adjust this frequency down just a little bit further. Oh my God, I've changed it. So I have to now save this. The only thing you can do is save as, and then with the same, yep, I want to override it. That's the only thing you can do. The interface of this program for stuff like that is, it was written by a Neanderthal, I'm sure. It's very archaic. But if you can get over those things, there are great things that can be done with it. So let me give you some recommended settings here. You're going to have wires. I, by a matter of habit, run odd numbers and quite often prime numbers in here. Does that matter? No. But I try to make sure that I have no less than 1 segment per inch in my antenna. Can you run more? Absolutely. Can you get away with less if you have to? Yes. But just for rough shooting from the hip modeling, try to make sure you got at least 1 per inch. If you got 2 per inch, great. Diameter. Diameter of your antenna makes a huge difference. So I'm going to go in and I'm going to look up an antenna that I was working on. Omni. All right, so this thing is a nightmare. Oh, that's actually not the right one. It's in here somewhere. There it is. So this thing is a nightmare to deal with. So this is an antenna that I'm currently working on for here at the shack. And as you can see, it's got multiple elements. This thing works on tons of bands. It does all sorts of stuff. But the diameter of each one of these elements is very important here. So you'll see here, I've got some that are at a number 14, and these are American wire gauge numbers, and they're in the copper series of American wire gauge. And I've got some that are in decimal inches because I'm running a larger copper tube for some of this. And I'm doing that because of some advanced tricks in antenna design. So let me run a plot on this and see. So I'm running my SWR happily, saying, hey, I've got this, you know, however many band element antenna that this is going to cover. Oh, wow. It won't let me do the SWR sweep. It says that I've got a negative calculated total power, and that this is locally a network with difficult values, and a network could be like a filter circuit. You can put those in here, or a source in a small loop. Well, small loop. What this probably means is that I have an eddy current in this thing somewhere that shows up at a particular frequency, and it freaks the math out, and the engine behind this thing screeches to a halt. So I don't actually need that frequency, so I'm going to go ahead and just look at this in another place and just say, and it's going to run through here, and it's going to tell me, okay, here is the match that I have on this antenna, which is immaterial. Just see that it's covering the ham band here with, you know, the repeater portion at the actual point of tune. All I'm going to do is I'm going to change the diameter of one of these elements, and I'm going to make it something much smaller, and we're going to run it again. So you saw that I had a really good match. I didn't change the length or anything like that. The only thing that I changed was the diameter, and suddenly I'm not matching at all. So when we're talking about recommended settings, there are times where you're going to change the diameter. Choose the diameter that you're going to build the antenna out of and run with it. When you get more comfortable with the program and you're trying to balance out complex designs, then you can start to get a little jiggy with it. But start easy. If you can, keep all the diameters the same, because in the program, as in real life, the diameter of your elements can make a huge difference. So here, I mean, you can see I've got a positive J 8.7 ohms. So it's very inductive. I wanted to add capacitance to this, but homie's not a fan of putting lumped elements into his antennas. They reduce the bandwidth, they reduce the efficiency. So that's where I just went ahead and said, okay, I'm just going to give myself more surface area. And then more surface area equated to a better match because that gave me capacitance that I could then utilize to bring my tune in line. And you can see that I'm still just slightly capacitive or inductive here. I could have gone for a little bit more capacitance, but I didn't want to because my actual impedance is high. So on the diameter, take note about that. I'm going to open another model and we're going to start talking about complex models. So this is a car, if you couldn't tell. I mean, I'm no artist, but I do what I can. And on top of this car is an antenna. So I'm going to zoom in on it. And then, so if you guys believe me that this is a car, you can see that the roof, of course, is just a grid. But there's a lot of stuff added here because when this was being put together, I was getting a lot of really funny results. And I was going, okay, this isn't right. I'm dealing with the geometry in the roof of the car. It's throwing me off. So here, when I go ahead and plot this, and you notice how slow it's going, that's because of how many segments are in this model. So if you add a ton of segments, understand it's going to slow your computer down. And this is just to run at one frequency. If I run the SWR on this, it's going to be horrendous. So now I got this really weird pattern. And I was going, what the heck is going on here? And I played with this thing for a good long time. And you know what? I'm not making 8.45 dBi of gain. So remember, I said, take those numbers with a grain of salt. And I fought with this thing and I said, okay, these are obviously the wires of the roof that are doing this. Why am I getting dead spots in my pattern? My elevations looking even weirder. And then it occurred to me, everything's right here at 0 degrees. What the hell is that all about? I had totally missed that the ground was perfect. So if I go to a realistic ground and we run it again, and again, the big takeaway about this is if you make big complex models, I've had antenna models in another program that can do much more than this one that I've literally had to let my computer run overnight and I come back the next morning and I can look at the pattern. There's a lot of math running back here. A Raspberry Pi ain't going to keep up. So, okay, things are starting to look more realistic now. Oh, 3.25 dBi of gain. Still probably more than it's actually making, but more realistic. So these settings can make a big difference here. So some other things that I had started to notice as I was going through this, and what I'll say is I took somebody else's model and I started using it without thinking what did they have set in it. So be careful if you do that. Make sure that the settings that carry over are actually usable. So ground description was wrong. The ground type was wrong. The actual wire is also still wrong because for this particular one, my wire losses would be steel, which isn't even listed in here. So I've got manual entries that I put in from time to time. So if I come in here and I add too many more segments, this thing won't even run. So let's get really ridiculous. I'm going to say I've got 60 segments in that thing. And now I'm going to try to run it. It actually passed the geometry check, which I'm a little bit surprised about. I was hoping to induce a failure there, but you see it's slowing down even further from where we were. So let's just go ahead and skip that. And I'm going to get really ridiculous. There we go. This thing has 2,302 segments. The maximum number permitted by the program is 2,000. Now, I do wish that they would raise this for the paid version of the program like this, but it is a hard limit. It is there, and with complex models, you're going to run into it. So just be aware of that. There's another mode of failure that you're going to run into here. So I'm actually going to scale this back to 200 so we can actually calculate it. But I'm also going to shorten my antenna up to very short. And I'm going to run it again. How did I pass the geometry check? Oh, it's because my connecting plane is wrong. All right, I'm going to jump out of here. And I'm going to open a different model where this will be easier to show you guys. Oh, okay, my Grid Madness antenna for next year. So again, this is a large, complex model. In this case, it's got a lot of individual antenna elements in it. And by the way, I made this in just a couple of minutes because when I go in here, I made the first couple of antennas, 4 of them here. And I said, okay, I'm going to come up here and I'm going to make multiple copies. And I got this window and I said, okay, I want to make 3 more copies of this and I want them offset, and I'm going to go the other direction. Let's go offset X, and I'm going to say negative 100 inches. So they'll go the wrong direction from my model so you can see them easily, and it's going to create copies and it's going to make them 100 inches apart. And boom, now I've got more arrays of my antennas out there. So if you're going to do a lot of work there, using those move and copy and stuff tools are going to be great. When we do, I think we're going to have to do another session on this for the people who really want to get deeper into it. We can go into that a little bit more. But, and actually, this is still going to be the wrong. What can I show you this in? There. This is my ground, or my antenna this year for Grid Madness. So if I take wire number 9 and I make it 10 segments long, when I go to run this thing, I'm going to get an alarm. It says geometry errors found, see geometry check window for details. You're going to run into this all the time. Just get used to it. The center of wire number 9 end segment is within wire number 5. It took me a while first playing around this program to figure out what that means. Here's what it is. If you make too many segments in one wire, so many that more than one segment is within the space occupied by the diameter of the wire that it touches, you'll get this alarm. So in this case, number 10 is a 1/2 inch diameter. So if I make 9 so many segments that any 2 of those segments can be within a 1/2 inch of each other, I'm going to get that alarm. And I ran into this all the time. And it was a real hassle. And that's where I started using that rule of thumb about the length of the wire to get the number of segments. So those are some of the common pitfalls here. So I'm actually surprised we went this long. I promised myself we weren't going to go too long on this. We covered opening, we covered saving, we covered some recommended settings, how I like the 3D plot. I like more resolution, so I go to 1 degree. Your alternate SWR, when you run it, all this does is it allows you to set a different type of feed line. So if I went to balance line, 300 ohm, what would my match be like? That's all that's about. It's not that useful of a feature unless you're playing in HF land and you say, okay, I can feed this with ladder line, window line, or 300 ohm TV feed line. Because then you can put in the different ones and see how you match, because that can make a difference there. Let's see, we went over far field plots and SWRs, sources, created some radials, went over some geometry stuff, and I don't want to get into the phases and stuff. You can make multiple antennas and phase them against each other like I had in that model I showed you that I'm working on for Grid Madness next year. But if we want to do an advanced session, we can touch on that stuff more. So really, the basics are more about getting a wire up there, putting a source in it. The wires have to be connected if you want them to be acted upon by the source. And it's going to act just like a balanced source, just like a balanced antenna source, like a dipole source would be. And there are some special stuff you can do up in here where you're going to do split sources and stuff. Don't worry about that for now. We can touch on that stuff when we get to a more advanced stage. But any questions on just the very basics of opening the program, punching in a few wires, and running some SWR plots and seeing your far field plot? Well, I see a few people asleep out there, but I see some people stirring around, but I'm not getting any questions. So I know that was a lot. I didn't think we were going to take this long, but I guess it just didn't occur to me that there is more to doing this than I think, because I do it so often that it gets second nature to me. So, you know, maybe there is enough material here to do an actual program in a meeting sometime or something like that. But that's only if this this little taste of it doesn't scare you guys away. Last call for any questions on this.
William, you know those the radial elements. If you were to increase from 4 to 8, what kind of improvement would that happen?
Very good. So let's look at our far field plot right now, and I'm going to take a look at our azimuth and see that right now we are 1/4 dB under 0 dB isotropic. And I'm also noticing here that my model contains loss. So I'm definitely not operating at my peak. So what I'm going to do is I'm going to delete the radials that we created, and I'm going to recreate them, but I'm going to go to the optimal, the peak. And actually, I'm not going to go quite that far because it's going to take forever to calculate stuff. I put 64 radials, so we're going to have a whole bunch of them now. So this thing ought to work pretty good, right? So we're going to go ahead and, does it still match up okay? Because, you know, your match is a big factor for your efficiency. And you see I added all those, and see how slow it now calculates the SWR. So that's where I said, be careful about how many segments you add. If I made each one of these radials have less segments, it would be less taxing on the computer. The model might be slightly less accurate, and that's a balance that has to be met. So, wow, I'm glad I didn't add all 120 radials of what would be optimal, because it would be taking twice as long as this. And I don't have a slow computer, so this tells you it's a lot of computational math to be done here. The math for this is actually running on my GPU, my graphics processing unit, which is a really good way to do mathematical computing. And I can crunch through stuff pretty fast, but I've brought this thing to its knees doing this before. How many more? Okay, it should have 10 more calcs to run. I should have thought up memorized some jokes for running these SWRs. Fill in the gap. I've got jokes, but actually we're not on amateur radio. I could tell the jokes that I have because none of them are clean, but you know, the FCC doesn't care in Zoom. All right, almost there. Okay. So we're matching really good here. Again, we're a little bit too low, and if we went back and ran this, which we're not going to do again, that'd take forever. You will know that when I ran this model, it went down. We were actually up here at 145, and it shifted us down. So that's because the antenna is being more efficient. The H field is coupling between the elements, and it's pulling it over and making a nice pattern much better. So we're matching well. We might have to tune it up a little bit if we're really trying to go to a different frequency, but let's go ahead and look at that pattern. So again, you see that it's taking a lot longer to calculate the pattern, but fortunately this is only done at one frequency, so it doesn't take as long as the SWR. And here's the pattern that we got out of it. And look at that. We gained 1/3 of a dB. And it's saying that the model still contains loss. So there's a lot of reasons the model can contain loss, not the end of the world, but that is the rub of it right there. Is it really worth cutting that many radials for something like this? That's why when antenna designers put together antennas that are going to go in the air, they do the 4-tuned radials, because that gets you a reasonably effective pattern, but it's not all that work to put together. You don't have all those materials costs there. But now if you are doing one on the ground, that's where it starts to make a difference, especially with these big, long, low frequency antennas where you're trying to use the ground to fill in the blanks and everything else. But in the design, I rarely run more than maybe 8 radials in the computer design. And the reason why I don't run more radials than I need to is simply because of that computational time. I can get, if you notice, the donut is looking the same as it did before. So I can get an idea, and that's all this program does, is it gives you an idea. You're not gonna cut to this exact length when you build the antenna. This is gonna give you an idea of what to cut that wire to. Am I really gonna cut it, 12.7 inches long? No. I'm going to cut it 14 inches long and then tune it and trim it back based off of what my meter is telling me. But it gives me an idea of what I need to cut. Those of you who got to see my Grid Madness antenna, you saw the design in here, and then you saw what the thing looked like on the end of the boom in front of the corner reflector. It gave me an idea of where to cut it. And in that case, I cut everything 1/4 inch long and then scaled it back because I had worked on that design for a while. But don't weigh yourself down. If you add too much, your computer just isn't going to keep up with it. And then the other thing is that I now have all those wires in there, and I'm limited to 2,000 segments. So if I want a big complex antenna, like the one I'm working on for next year, I'm going to run out of segments available in the modeling before I ever get there. So don't overdo it. Great question, though.
This is really fascinating. Incredible. I don't understand much of it, but it's fascinating to be able to do this. So is there a way that you could configure a physical antenna and then optimize it?
Well, what do you mean?
Well, when we used to design amplifiers, we configure an amplifier with capacitor, inductors, and transistors and everything, and then we just change the parameters to optimize the gain, the amplification. Can you do that with antennas too?
Yeah, a bit. Oh, I've got these sorted by date. Let me find a newer antenna. So here is my house, and on here is an antenna. And what I did, this is the storm resistant antenna that I put up when Douglas was coming through. And I put in the house to see how it would affect the pattern, and I moved the antenna around on the structure till I found the wavelengths in resonance that I wanted, and I found a usable pattern that I found effective. So that's a way that can be done. Another way that can be done, if we come back here and we look at my Insanity from Grid Madness this year, this is the antenna that I used for Grid Madness. And here, if I look at the far field plot, this is, I can take this in the model and I can say, okay, I've already built this antenna. Some of you guys saw pictures of it. It was in real life. This antenna was there, and it was in front of a corner reflector. But if I move it in and out, different distances, what does that do to my pattern? Because I was trying to optimize a couple of things. I wanted gain towards Oahu, and that's what this gave me, was gain towards Oahu. But I was also operating on 3 different bands, and the optimal distance for one band is not the optimal distance for another band. So I said, okay, I'm going to set it here, and now I'm going to come over here, and I'm going to look at another band and I'm going to see what this distance does for there. And I was able to find the happy medium to be able to run 3 bands and get 3 usable patterns. And this is sort of a funky pattern, but it's got a great lobe forward, almost 12 dBi of gain forward. And the reason why it's offset side to side like this is because there's all sorts of different elements off of this antenna because it can work on multiple bands. But I found the distance that worked on the 3 bands that I wanted to use. So I designed the antenna initially without this because I knew that I needed an antenna that would operate on all 3 bands. It would match up fine on all 3 bands. And then I said, okay, I want to get a lot of gain. How can I do that? And then this is how I ended up with 16 1/3 dB of gain, which, again, take those numbers with a grain of salt. But I found the right distance to maximize that forward lobe. So that's a way that that can be done. So, and then if you're interested, this is what that thing looked like without the reflector on it. And that's why the pattern was so weird, is because at 220, it's using this element and this element, but these elements are also coming into play. These are the 70 center elements, and it's kind of pulling that thing off to the side on that one side. So I designed this because it did what I wanted it to do, and then I stuck it in front of that corner reflector to get the gain that I wanted. But this is the this is the proof that if you do your math right, you can have one that works at 2 meters, 1.25 meters, and 70 centimeters. And these dips go a lot lower if I run at higher resolution at each one of the bands. But so that's how I was able to use one antenna for all 3 bands during Grid Madness. And it was only possible because of this program. Could I do it by hand? Yeah. Am I going to do it by hand? No, never. So because the program, I was able to take the antenna, say, okay, I can build this reflector. How can I position this? And instead of doing it in real life and trying to take measurements and stuff, I said, oh, okay, roughly this distance, this angle on the reflector. Okay, there we are. All right, any other questions?
Yes, I have a question.
Go ahead, Jim.
The segments, when the segment numbers, that's how many you break each line up into, right?
Correct. So each line, it's going to take measurements this many times along the lines. So that's the segments. You can consider those little wires that make up a longer wire. The more segments, the more resolution you get.
And you typically run, like, how many segments would you?
When I'm just spitballing an antenna, shooting from the hip, I try to go with about 1 per inch for a VHF antenna. It's actually a ratio based off of the wavelength, but just keep yourself to a rough, 1 per inch for your VHF antennas. For like a 160 antenna, 1 per inch isn't going to make any difference. The 160 meters doesn't care. You could run them 6 inches apart and you're going to get the same result. But if you go less on a VHF antenna, if you go less than about 1 per inch, you're going to start to see differences in your calculated SWR and your calculated field strength. So it gives you enough to get by, but without overdoing it in the computer.
The reason I ask is because the free version limits you to 20 segments.
Total?
I just said, it said 20 segments. It didn't, let's see.
20 segments or 20 wires with 20 segments per wire?
Even with the 20 segment limit, the demo program does a very respectable job. It doesn't say, okay. Standard program is that the demo program will have 20 segments, which limits the complexity of an antenna you can analyze.
Yeah, so you're going to get away with some dipoles, some stuff like that. You're not going to pull something like this off out of that free version. I haven't used the free version in so many years that I had forgotten that it was limited like that. I thought it had a limit on the number of wires or something like that, but yeah, 20 segments, you're a little limited. You're going to do HF stuff just fine, because again, you don't need that many segments at HF, but for the higher band stuff, you're going to need more segments than that
Yeah,
to really get effective.
Yeah, I kind of mistook segments meaning line sections rather than
Yeah,
breaking.
you thought about it in the CAD term like I initially did.
So, but to model, say, if I wanted to model my NFET as it sits at my house, I should be able to do that with the free version.
Yeah, because you're down there in HF, you're going to have, you're going to just understand that your SWR may actually report a little bit higher than you would anticipate, and you may end up showing a little bit less gain than you might actually get, because that's a lot of segments over a lot of space, but at the HF frequencies, that'll work.
Okay, thank you.
Mm-hmm. And remind me, if I ever send you models, to send you segment limited models, because if I send you one with 1,800 segments in it, it's going to be a problem.
If I really get into it, I'll just end up buying it because I think it was it like $100?
I got it so long ago, I don't remember, but I remember for me, even just playing around, it was worth it because I love doing this stuff. I do this professionally a little bit, but not nearly as much as I would like, because if I could just design antennas all day, I would do that. I would happily sit here 16 hours a day and design antennas and just be giddy. So, all right, any other questions?
I have a question, Will.
Go ahead.
Okay, so you can use all the different types of materials, copper, aluminum. I notice you have wire gauges and all that stuff. In your opinion, what would be the optimal thing to model? You're gonna build an antenna. What would you recommend using as a good material base?
Well, what are you going to build it out of?
Well, that's the question. Yeah, I mean, because there's so much different. You got copper, you got wire, you got aluminum. What would be the one to use most of the time?
So if you're just going to model an antenna and you don't know what you're going to build it out of, model it in aluminum in the program. It's a good middle ground. So here, I'm going to go to zero loss, and I'm going to look at my gain here for 70 centimeters. And it's going to say I've got 9.29 dB of gain if I've got zero loss in the wire. So now I'm going to come back here, and I'm going to go to zinc, which is horrendous. And I'm going to rerun that antenna as if it were made out of zinc or zinc-plated wire. And I can even see the shape difference in the pattern there, 928. So not a great difference for the actual lobe, but I did notice a shape difference here. So it'll make a difference, but where you're really going to get the big difference isn't in the gain as much. It's going to be your SWR. So let's look at something lossy. So this is a larger model. I'm going to cut it down. Okay, so here it's saying that up at 450, I've got 65.32 ohms and 1.46 on zinc. So let me go 0. And here it didn't make a huge difference. This is just telling me this isn't the right model to show that in. You can see pretty significant gains or losses in SWR between going with a high loss wire and a low loss wire. Simply being, if it's acting like dummy load, it's going to match better, right? So again, good middle ground is aluminum. You may end up making a lot of stuff out of aluminum. Copper, of course, performs better because it conducts better. There's less loss in it. So for really crazy stuff, copper is often common. My personal favorite for building HF wires is copper-coated stainless steel, which is really hard to get your hands on, but it's got the strength, it's got the corrosion resistance, and it's got the conductivity because of the skin effects using that copper. So I would choose the wire that you're intending to use. If you don't know what you're intending to use, just use the middle ground of aluminum. All right, any other questions?
Why do you say that the copper-coated iron is so difficult to get?
Well, copper-coated steel is easy to get. Copper-coated stainless steel is a nightmare to get. Copper-coating stainless steel is not easy, number one, because stainless steel has a passivating layer. So it's not a commercially available product. Generally, I've had it done as a batch product, and only certain platers are willing to do it because if they don't really trust their skills, then they're worried that the copper is going to come off. But in our environment, now it's not so much of an issue that VOG's not an issue at the moment, but when VOG was a big issue, if you put up an aluminum wire, you can have some problems. If you put up anything that's really susceptible to corrosion is going to have problems. Whereas the stuff that I built out of the samples of copper-coated stainless that I had performed well, and they're still up now. I mean, they hold up to the test of time, in my opinion. So it's a, but I mean, sometimes I get into the nitty gritty. I'm trying to squeak out that last 1/10 of a dB, because if I can find a 1/10 of a dB in 10 places, hey, I got 1 dB back. But does that 1 dB really matter in the grand scheme of things? No, absolutely not. For me, it's just the game. You know, I'm trying to get absolutely as much as I can out of it. That's why my tuner is at the feed point, and that's why I'm running, you know, high dollar, you know, 1/2-inch foam core coax even on my HF stuff. The loss doesn't matter there, but you know, it's about taking it to the absolute extreme.
This looks like a lot of fun, though. Gosh.
Oh, it can be.
You know, when I was working for the phone company, I forgot what they call it. I don't need to call it C-wire, but it's the wire that goes from the pole back down to the house, and it's either iron or I don't think it's steel. It's probably just iron.
It's copper. It's copper-clad steel wire.
Steel wire. Okay.
Yep, copper-clad steel.
Yeah. So there's a whole bunch of stuff sitting up in the poles right now.
Mm-hmm. And actually, I've used that stuff effectively as balanced line many times, because it is a balanced line. You can use it as a feed line.
Oh, okay. So it's like a ladder
Yep,
wire. Then.
exactly.
Yeah.
But I think its characteristic impedance is closer to something like 75 or 100 ohms or something like that, because those wires are really close together.
75 sounds very familiar.
Yep. If it conducts electricity...
Thank you very much. Boy, this is really interesting.
No worries. If it conducts electricity, at one point I've tried to use it as an antenna or a feed line. I'm sure of it. So, all right. Any other questions? All right. Well, sorry it took longer than I anticipated, and you know, barely even scratched the surface of this topic.